Well, hello, welcome back, wonderful physics students. I wanted to continue the conversation on Coulomb's law with you and talk about some more aspects of it. Okay, so let's begin. We have this equation. The definition of the electric field is given by this equation F equals QE, where E, the electric field, is the force that 1 coulomb of charge would feel if it were placed in this location. It is not, Q is not the charge that is causing the electric field, and we will get practice with this as well. What is really important here is that would feel if. The electric field is a force that 1 coulomb of charge would feel if. Would feel. So this doesn't have to be 1 coulomb. If it is, then this force and this electric field are the same value. All right, so let's get some more on this. So what if the charge, so this is going off the previous example. So if a charge were the same but negative, so we're going to put a negative charge at this point right here that we know the electric field. Okay, so we know the electric field. We know it has some definite magnitude and direction, and we have a negative charge. The force felt by this charge right here, where did I go, is equal to, or is in the opposite direction. If this was a positive charge, it would feel it in the same direction as the electric field, but since this charge is negative, it feels it in the opposite direction. And these are the numbers from last time. We'll work out more examples coming up here shortly. So what if a charge were placed somewhere else? So we have a charge, and on these PowerPoints and what we will be doing now, the negative charges are always pink, positive charges will be green for us. So if a charge was placed somewhere else, but we know the electric field right here, can we say anything? We don't know. We don't know. For us to be able to use this equation that we're given, the only one we have so far, F equals QE, where F is a vector and E is a vector, the only way to use that is if we have the electric field and the charge at the same point. If they're not in the same point, we cannot use this equation. We just don't know anything about the electric field right here, and so we don't know anything about the force on this charge at this location. Okay, so you may be asking yourself, well, okay, but how do we find E? Like, that would be really useful if, otherwise we have to know what E is at every single point. And if we could find a way to find E, that would be really useful. Well, you're in luck. So F equals QE. F is the force on the charge Q, this charge right here, due to the electric field at Q's location. Q is the charge that is feeling the force, the test charge. And E is the field at Q's location due to other charges, some other charges around, not at that location. And those are called source charges. Okay, so let's work out this example. A charge of -5 times 10 to the -8 coulombs feels a force of 0.2 newtons to the right. What is the electric field, magnitude, and direction of the at the charge's location? All right, I would like you to pause the video and work this out. Welcome back. Okay, so since this is a negative charge right here, we know the electric field and the force go in opposite directions. If this was a positive test charge, they would be, force and electric field would be in the same direction. But it's negative, so it goes in opposite directions. We use F equals QE. So if we solve this for E, E is equal to F divided by Q. we plug in the numbers. Now notice this magnitudes are always positive. Right here, magnitudes are always positive. The directions given in either words or by an angle. Okay, so if you're having trouble with the scientific notation, just make these easier numbers. Let's say a charge of -5 coulombs feels a force of 15 newtons. So then you would do 15, the force, divided by the charge 5, and you would get 3 newtons per coulomb. So don't let the scientific notation throw you off. Okay, what direction is the electric field at point X? So remember, electric field is the force that a 1 coulomb charge would feel if it were placed at that location. So let's say that we had a 1 coulomb charge right here. Now this 1 coulomb charge doesn't actually exist, but we're just going to say what would happen if. So we have positive charge and a positive charge. They repel each other. So our force would be this way. And since this is a positive charge and the force is this way, oops, I want a blue. There we go. The electric field is this way. Okay, now I don't know which one's bigger, force or electric field at this point. Actually, since this is a 1 coulomb, they should be the same length. Okay, all right, so let me erase this. So electric field is that away. So now let's do the same exercise with a negative charge. So remember, the electric field is the force that a 1 coulomb charge would feel if it were placed at the location that you are concerned about. So we're going to put a 1 coulomb charge here. This is a positive charge and this is a negative, so opposites attract, like Paula Abdul says. So this is a force this way. Since this is a positive charge at the point that we're dealing with, the force and electric field are in the same direction. So electric field would be to the left. Okay? A way to remember that is that positive, the electric field goes out of positive into negative. Okay, so the electric field's to the left. How big? How do we calculate this, you might ask? Here we go. Here's our equation. E equals KQS over R squared. S stands for the source charge. So test charges always reside on the point that we are concerned about finding the force. Source charges lie somewhere not on that point. This charge is providing the electric field in the space around it. So having a charged object affects the space around it. It can attract or repel other charges. And so to solve for the electric field, it's this constant, K, which is 9 times 10 to the 9th, newtons meters squared over coulombs squared. This right here is just the units. It's a messy units, and the only thing you really have to be concerned about is the number 9 times 10 to the 9th. QS is the source charge right here, and R is the distance from the source charge to the point that you are concerned about. You have to square it. Now, this is only good for point charges. Only do this for point charges. All right. So let's work out an example. A 2.5 times 10 to the negative 6 charge is placed as shown below. What is the electric field at a point 5 centimeters to the right? before you start, I want to talk about a couple things here. You're going to be using a lot of scientific notation. Our charges are generally going to be very, very small. Anything that is times 10 to the negative 6, this is micro. So you could write it as 2.5 microcoulombs, which is equal to 2.5 times 10 to the negative 6 coulombs. It's the same thing. All right, so we're going to have to do that. Be aware of that. 5 centimeters. We're going to have to always work in meters. So 5 centimeters is equal to 0.05 meters. So you will have to convert that before you start. So okay, so now you have the tools. Go ahead and work this problem. Welcome back. Okay, so the first thing is, which way is the electric field? Well, electric fields go out of positive, so the electric field is going to go to the right. We use the equation E equals KQ over R squared. So we plug in the numbers. K is 9 times 10 to the 9th. Q is given as 2.5 times 10 to the negative 6. And the distance, 0.05 squared. 0.05 is the same as 5 times 10 to the negative 2. Plug that into your calculator, and you get 9 times 10 to the 6 newtons per coulomb. And the direction, which way does he point? Correct, to the right. All right. Now, let's say we want to find the electric field right here, which is also 5 centimeters away, from this charge, but on the other side. Well, this equation stays exactly the same. K is the same as a constant. The source charge is the same. It's still 2.5 times 10 to the negative 6. It's still 5 centimeters away, so you're still going to get the same number. But the electric field is always pointing away from this positive charge. So this equation right here does not tell us anything about the direction of the electric field. You need to draw your pictures and draw your vectors out. There is no way around it this time. A negative does not tell us direction anymore because the geometry, which way is positive? Any of them could be positive, or they could all not be positive. Okay, so in conclusion, Coulomb's law, E equals KQ over R squared. It's going to be your friend. We're going to be working a lot with it. And we are done. Oh, so when you work this equation, you always want to use absolute values for your source charge. Get your directions from your pictures. All right.